Welcome viewers to the 8th lecture of spur and helical gear cutting. So, up till now we have discussed simple indexing and identified some problems of simple indexing, like there might be some numbers of teeth for which simple indexing would not really work, or you would require some an assortment of index plates in order to achieve simple indexing in such cases. So, there can be other solutions to these problems, and let us quickly go through such examples. We had been discussing about 40 by 33 being unachievable. That means, suppose I do not have a 33 hole circle. So, you might say that is it really possible that you do not have 33 hole circle? This is just by way of an example. There might be other numbers of teeth, like suppose you have 87 or 265 or something like that, which is not there. Okay. So, we are taking a problem where this particular whole circle is not there, and we say that if that denominator can be broken down into its respective factors, then we might be able to employ the method of partial fractions and achieve something called compound indexing. That means, this rotation which is required, which is 1 and 7 by 33rd of a rotation, that will be equal to the algebraic sum. Okay, they might be having different signs also, algebraic sum of these two. What is the restriction of A and B? First of all, A and B are whole numbers, and they have to satisfy this particular equation. So, in that case, I mean they are integers, they have to satisfy this. So, what we can say is that if this be so, we can easily let us look at the piece of paper. We are having 40 by 33 is equal to A by 3 plus B by 11, and therefore, if we take a summation of these two, 33 in the denominator, 11A plus 3B. Okay. There are elaborate ways of finding out the possible solutions of A and B, and finding out the number of whole circles which will be employed in these cases, but at this moment we are not going for such an elaborate discussion. Compound indexing is not that popular because it essentially combines two different successive rotations. We would always be interested to work with a single movement, less number of movements to achieve the required rotation would result in less amount of errors. So, this one means that 11A plus 3B should be equal to 40, and by the method of trial and error, okay, you can easily hit upon some solutions. This is basically the equation of a straight line. A and B have to be integers, and so let me suggest, suppose A is equal to 2. So, 11 into 2 plus 3 into 6, how much does it give us? 3 into 6 is 18 plus 22 equal to 40. So, this means that if A be equal to 2, 2/3 rotation plus 6 by 11th of a rotation, these two separate rotations will give rise to 40 by 33 of a rotation. What does this mean? This means that suppose I employ any particular value, say multiple of 3, how much, say 30. So, on a 30 hole circle, so 20 holes on a 30 hole circle, plus 6 holes on a 11 hole circle. This will be the same as 40 by 33 of a rotation. So, that means first of all I rotate, let us go back to the previous, just a moment, that is it. First I take out this pin from the index plate and rotate this by say 20 holes on a 30 hole circle and put the pin down. That means I am sealing this particular initial rotation, 20 holes out of a 30 hole circle. Put the pin down, and after that if I still rotate, the index plate is going to rotate with us. Why are we doing this? Because now I am going to keep track of the rotation by the help of some other fixed device. Suppose I put a pointer here, okay. With respect to this pointer, now this particular index plate is going to rotate with respect to this say fixed pointer. The index crank is now going to rotate. So, first move by 20 holes on a 30 hole circle. Now, with respect to the pointer, with the pin inside the index plate also rotates after this, and with respect to this particular pointer, make sure that you move by 6 holes on an 11 hole circle. So, both these hole circles have to be present on the same side of the index plate. This, after this is done, the net rotation will be 40 out of 33. So, this is called compound indexing. Now, there is yet another method in which we might be having the use of feedback. So, indexing with feedback is called differential indexing, and let us have a quick look at it. What does this figure show us? This figure shows us once again. So, let us go through things that we already know. Just a moment, have we missed something? No. Things that we already know. This is our index crank, this is our this worm axis, okay. This is the worm axis, this is our worm gear, this is a pair of bevel gears which turn the rotation by 90 degrees, okay. And we find that there are some gears now existing which rotate the index plate. In simple indexing, we had not rotated the index plate. Index plate was remaining stationary. With respect to the index plate, we were counting off our rotations of that particular index crank. Now, what we do is we have differential motion of the device. Differential motion means that the ultimate motion is the difference between two motions. One motion is the direct motion of the index crank, and the other motion is the fed back motion of the index plate. Due to the difference of these two motions, we will be achieving our required amount of motion. So, let us see that in this particular view. This is the view of the front view of the index plate. This is a starting hole, okay. This is a starting hole. From here, this is the next hole which is actually existing. Let me draw a figure so that this would be easier to follow. If you look at the index plate, this is your index plate. On the index plate, this is say a starting hole, and this is the second hole, this is the third one, etc., etc. Now, you might say, which hole circle are you talking about? So, let us define the problem. Previously, if you remember, we were talking about cutting 70 teeth. Now, the problem is slightly different and more difficult. 71 teeth have to be cut. 71 teeth have to be cut. Had it been 70 teeth, we would have used simple indexing. There would not have been any problem with that. Now, the problem is 71 teeth have to be cut, What's the problem? The problem is 71T whole circle is not there. 71 whole circle is not there at all. So we know the magic number 40 by 71, rather 40 by 71st of a rotation has to be achieved on the crank handle. In order to achieve 1 by 71st of a rotation on the gear, 40 by 71st of a rotation has to be achieved on the through the crank handle, index crank. If you don't have 71 whole circle, this is next to impossible. So what do? We find out some whole circle which is quite near to 71. So for that, suppose we identify this is the 70 whole circle. This is the 70 whole circle, not the 71. 71 whole circle is not there. And suppose we define this one as our starting point. Say this is the center. 70 whole circle, first circle. 70 whole circle, second one. So if I now ask you, what is this amount of rotation? You will say, why? This is 1 by 70th of a rotation. 1 by 70th of one full rotation. Yes, I accept it. Now, had there been 71 holes, okay, then the second hole, if this is the first hole of that virtual 71 hole circle, had it been present, the second hole would have been somewhere very close and ahead of the second hole. So this I am drawing as the virtual second hole, which would have existed had I had the 71 whole circle. First hole, second hole of the 71 whole circle. It is not there. So my plan is, in order to get it here, it is virtual. Things which are virtual, they are not tangible, you cannot touch them. You dream of things and then they disappear, something like that. But I want it. You will say, I want it here. What do? You bring this one here. While you have started your movement from this point, as you just reach this point with your crank handle, this much amount of rotation, in that time you import it to this point. So you will find a hole and you will get inside it. This is differential indexing. The whole index plate will be rotating backwards while you have put up your crank and you are moving like this. You are moving like this. In that time, this whole plate will be moving this way, so that this one comes to this point. That is it. That is what we are going to achieve. This is the basic idea of differential indexing. Make the plate move so that you achieve what you want. You get a hole in the location that you want. Coming to the figure now, let's see how this is physically implemented. Physically, we see that there is an addition of a gearbox. Now all those discussions that we had about gears and gearboxes, etc., will now become quite relevant. What we have done is, since I want to rotate this index plate, I am tapping motion from the worm gear, putting in a gearbox, okay, some ratio, I do not know that. I will find out what should be its ratio, and I am simply rotating the index plate backwards or forwards, whichever be the case. How much is the amount of rotation required from the index plate? This much. That is what we have calculated. Okay. How much is the motion of the index crank during that time? This one, and totally they make up 1 by 70. In the general case, 1 by n available. So let us do the calculation now. Okay. We do the calculation this way. The crank, how much does it rotate? first hole, second hole, virtual hole. This is the crank rotation theta. Rotation of crank, okay. This is not readable, crank rotation theta. This much, okay. How much is it? This must be equal to 1 by the number of teeth to be cut. This is the virtual hole position, and this must be equal to 1 by 71 in our case, okay. So, we write 1 by 71, and in the generalized way we write 1 by n required. Both are correct. This is specific case, this is the general case. Next, from this one, where are we going? If you look at the figure, this is going to directly, this amount of rotation is directly going to the worm. So, we need not worry about the worm rotation, but we can worry about the worm gear rotation. Worm gear rotation must be related to this. This is basically equal to, we will write equal to worm rotation. So, the worm gear rotation must be equal to a fraction of this, 1 by 40. So, we have 1 by 40 into 71, and the generalized case is 1 by 40 into n required, okay. Specific case, general case. From the worm gear, we are moving on to the change gears. So, we say, so this must be input to the change gears. We write input to gearbox, and gearbox is having ratio unknown. So, ratio u we write, and therefore, the output of gearbox must be equal to, just multiply u with that, because we know that this must be equal to output by input. So, this one into input must be equal to the output. So, we write u divided by 40, now just a moment, into 71. General case, u divided by 40 into nr, and this is input to index plate in a 1:1 ratio. So, see this same value is input to the index plate, and what is the index plate rotation? This amount. So, this must be equal to this, say let us call this alpha, equal to alpha. So, we make this particular equation now. This thing is equal to alpha, and what is alpha? Alpha must be the difference between n available, 1 by n available minus 1 by n required. So, let us put that here. Alpha is equal to 1 by n available, this one is 1 by n available, and this one was 1 by n required minus 1 by n required equal to n a into n r minus n a. Okay. So, this must be equal to this value, equal to u by 40 into n r, and therefore, we have from this one, let us copy it to a different sheet of paper. Or write it here itself. cancel this out and you get the relation U equal to 40 into NR minus NA by NA. That is it. So, I can state, so the value of U has been exactly calculated, and therefore, we can state, if we come back to the figure once again, if I set the change gear ratio, this being the input side and this being the output side, if I set the change gear ratio to a value 40 divided by NA multiplied by NR minus NA, in that case I will exactly achieve a backward rotation of, not backward always, anyway a resultant rotation of the index plate, so that I will be achieving exactly 1 by NR rotations on the gear blank. This is the most general statement that we can make. Okay. That is, this change gear ratio, if it is set to 40 into NR minus NA divided by NA, in that case it will result in rotation of the index plate, so that a rotation of 1 by NA on the index crank will result in 1 by NR rotation of the gear blank, and that is what exactly we want. Now, for the specific calculation, let us apply this. Therefore, U for NR equal to 70, sorry, I am making mistakes. For NA equal to 70, NR equal to 71, this is our requirement. U must be equal to 40 into 71 minus 70 divided by 70 equal to 4 by 7. That is it. Seems to be very simple. 4 by 7. If you can put such gears with the ratio 4 by 7 in between the worm gear shaft and the index plate shaft, you will be achieving differential indexing in this case. So, we will be definitely doing some problems during the problem session, and let me define them so that you can think out the idea and we can compare our results during our questionnaire session. For example, suppose you have to cut 83 teeth. 83 teeth, and the 83 whole circle, sorry, let me frame the problem this way. Problem, you have to cut 83 teeth, 83 whole circle is not here, not present, not available, not present. Okay. And the nearest available one, nearest available one is 43. Why 43? I could have given you 80. Here the idea is, if 43 is present, you can do the calculations with 86 in mind, okay, with 86 in mind, and after that you will find that 2 will cancel out, so that ultimately you can work with 43. So, this is also another thing that we will be learning. Exactly the nearest whole circle might not actually be present, but with its virtual presence you can do the calculations, and after that you might find that a fraction of it, if it is present, that will do the trick. So, this one, please work this out, we will carry out the calculations during our questionnaire session. Okay. So, after this, so I will be giving you more problems of this type when we discuss further. Now, for a quick look at what we have discussed, so that our doubts, if any, will be clear. I have tried to, those people who have had troubles in following the three-dimensional pictures, I have tried to give the explanation of the thing in a flat two-dimensional drawing. Let us have a quick look at it. This is our index crank. When you are rotating the index crank, this is the shaft of the index crank which goes right through to the worm, and the worm gear is shown here, okay, like this, and it has its shaft on one side, it is carrying the blank, on the other side it is carrying the change gearbox, and the change gearbox output is given to the index plate through a pair of bevel gears, and the index plate rotates due to that. So, this is a typical figure which has the details of a gearbox for differential indexing. This is the calculation that we have worked out. So, I am not doing it once again, just a moment. There might be a mistake in, not a mistake, the one difference in sign is there. I have written in a difference in R to generalize the case. Now, question is, the operator who is carrying out the differential indexing, he might say that, okay, so far so good, you have put a particular gear ratio and we are expecting that cutting will be done quite properly with that, but how much do I rotate the index crank? If 71 teeth are to be cut and 70 whole circle is available, how much is the rotation that I give? The rotation will be 40 by Z, that means 40 by available. On the available whole circle, if 70 whole circle is available, you will be moving by 40 holes, and automatically the machine, due to the presence of the gearbox, will be converting it into 1 by NR on the workpiece. So, 40 by NA will give rise to 1 by NR. So, on a 70 hole circle, move by 40 holes, and the rest will be taken care of, all those gearboxes and other things that we have put in between, that is it. Okay. So, the rotation is 40 holes out of 70 hole circles. Now, I will just introduce the idea of milling of helical gears. We have studied about differential indexing. Instead of going for solution of numerical problems, I will introduce the idea of helical gear, and later on in our 10th lecture, 9th and 10th lecture, we will solve numerical problems. Let us have a quick look what we are trying to convey through this particular figure. This is the table of a universal milling machine seen from the top. This is a horizontal column and knee type universal milling machine. Why horizontal? Because this is the axis of the cutter, okay, axis of the arbor which is holding the cutter. Arbor is the shaft which is holding the cutter. This is the cutter. Now, how does it correspond to the cutter that we have seen in our drawings? This is that rotary disc type cutter. The disc is being seen from the top, not the circular part. I mean the width of the cutter is seen in this direction. Okay. In the other view, if you look along the arbor, you will see a circular part with the teeth on its periphery. So, how does the cutter move? It rotates about the arbor to develop cutting speed. And what are the other types of movement that it has? Relative to the table is going to have movement this way. The table has movement this way. What other movements are being provided here? The cutter is being rotated. The cutter is being rotated. So, that means across, previously we were having the cutter here and the table was straight, okay, and the table was simply moving to and fro, so that the cutter cut right across, cut a groove right across on the circular or curvilinear surface of the workpiece, the cylindrical surface of the workpiece. At this moment, the vertical plane containing the cutter is at an angle defined by the helix angle, okay, is at an angle with the workpiece. Why is this so? Because we have to cut a groove which is a helical groove on the surface. So, for that let us have a quick look at this figure. The basic idea is, if you have to say put a pencil mark on a cylinder in the form of a helix, the helix is moving this way, which means that at a particular moment it can be defined by a definite velocity this way and a definite velocity this way. So, that the resultant is always tangential to the helix. How is this possible? You can put a pencil here, suppose I stick a pencil here, give a rotation to this particular workpiece or a cylinder, and move the pencil actually at the same time. Okay, I am holding the pencil, I am moving the pencil this way, and at the same time I am rotating this particular body. You will have the cutting of the tracing of a helical line on this one, on this particular cylinder. Same thing for the cutting action during helical milling of gear teeth. We have rotation of the workpiece, okay, giving the rotation for the helical motion, and straight line motion of the workpiece. Okay, straight line motion, these two combine to provide relative helical motion of the cutter with respect to the workpiece. But then why are we rotating the whole table about a vertical axis? Why is this particular thing inclined? We could well have done the whole thing with the cutter in this, with the table in this direction. That we will discuss the next day. Please have a thought about it. Okay. So, this way we come to the end of the 8th lecture. So, after that we will be taking up the discussion of the this is the 8th lecture. In the 9th lecture we will be discussing the rest part of helical milling and all the other things that are left behind for milling of spur and helical gears. Thank you very much.